Can you unmute?
Am I audible?
Yes, yes.
Okay.
Good morning, everyone. A warm welcome from einfochips. Thank you for joining this webinar on evaluation of CMOS technologies and its impact on future semicon devices, presented by einfochips and IESA Gujarat Chapter. Today we have Dr. Nihar Mohapatra with us. He has done his PhD in microelectronics from IIT Bombay. He is currently professor at IIT Gandhinagar and works in area of microelectronics. He has unique combination of industry experience and academic research in field of semiconductor. He worked for Global Foundries in Germany as well as IHP. His work is published in journals and conference proceedings. Now, I would kindly request Dr. Nihar Mohapatra to continue our event by sharing his valuable knowledge with us.
Okay, so good morning, all of you, and I am very sorry for this disturbance. So before I start, so let me thank the einfochips team for inviting me to talk to you. So I think all of you could hear me properly, and if not, please let me know. So today I will talk about evolution of CMOS technologies and its impact on semicon devices. So coming to the CMOS technology, so Deepesh, can I go to the next?
Yes, sir. Yes.
It's not going, I think. Okay. All right. So actually the talk is not going. So here the okay, so the talk is about CMOS technology. So CMOS, I think all of you know about it. The CMOS stands for complementary metal oxide semiconductor. And CMOS technology is the technology where the ICs, the integrated circuits, are built by interconnecting N-type and P-type MOS transistors. So if you go to the next slide here, so here as mentioned, so CMOS is nothing but NMOS and PMOS together. So this slide shows the PM micrograph of a CMOS circuit. So here in the bottom, I think no, whether you could see. So in the bottom here you could see a NMOS. So can I go back? Can I go back? No, next slide, please. Yeah. So here, here this is the TA micrograph. In the bottom, you could see a NMOS transistor, and also here the PMOS transistor is not shown, but you could see there is also a PMOS transistor. If you go to the right, there is a PMOS transistor. So CMOS technology is nothing but integrating NMOS PMOS transistor, interconnecting NMOS and PMOS transistor through a plethora of interconnects to form different circuits. So if you go to the next slide. So I'll talk about how the CMOS technology has evolved over the years. So these are the three things that have shown in the left hand side, that is a microprocessor, a DSP processor, and a memory ICs. So the invention of these three things actually started the CMOS technology revolution. So this enabled the application. I mean, this enabled the use of CMOS circuits in various areas, right? So here I am mentioning few of them. So like automobiles, communication, healthcare, entertainment, and also in the in the industry automation. So if you go to the next, also you'll see the CMOS technology nowadays are used in smart farming and also, as I discussed, healthcare. If you go to the next slide, please. Further, to understand the increased importance of the CMOS technology, we need to know the way the digital domain has evolved over the years. We started with mainframe computing, where multiple individuals are using one machine. Then we move to personal computing. So where there is a connection between one person and one machine. And also then we move to mobile computing, where one individual is accessing multiple machines. However, we are now in the era of ubiquitous computing. So here the machines are connected to each other. The machines are connected to each other, and the computation is embedded in them. Right? So the machines talk to each other with or without help of human beings. So these kind of systems that we're talking now needs lot of sensors, sensor interface circuits, and low power computing nodes. So hence the demand of CMOS technologies in future is going to increase because of advent of ubiquitous computing. So if you go to the next slide. So these are some of the examples. Okay, if you go back, sorry. So these are some of the examples of multi-machine, multiple machine interfaces like IoTs, self-driven cars, also our mobile system. So if you go to the next slide. So here I like to give this example. So this the slide tells you how the CMOS technology has evolved in last 25 years. So this is a special slide. So I have chosen these 2 years, 1997 and 2022. So because in 1997, this is the first time I used a computer when I was my BTech second year. So you see, in 97 we had Intel Pentium 2 processor, and in 2022. Now Intel Core i9 processor this processor is recently launched, actually 2 months back. So if you compare these two processors, these two microprocessor, so the left hand side, so Intel Pentium 2, this is a single core processor having a clock rate of 230 megahertz to 450 megahertz. The die area of around 195 millimeter square, a number of transistors 7.5 million. But if you look at the recent microprocessor, recently launched microprocessor, so it's a 24 core microprocessor, 3 gigahertz clock rate. But the interesting thing is, look at the die area. So die area here is 253 millimeter square, and the number of transistors that we're talking about is 12 billion, right? So if you look at the density, the transistors per millimeter square in both these processors. See, in one case we have 35,000 transistors per millimeter square, which has increased up to 50 million transistors per millimeter square, right? So this is how the CMOS technology evolved in last 25 years. But CMOS technology is there, so is there from late 1970s. So if you go to the next slide. So, so this graph here shows the evolution of transistor count. So basically, I talked about in the last slide about the transistor density. So this transistor density tells you that how many transistors are there per millimeter square of area. So here you see there is a steady increase in the number of transistors, the transistor density over the years. Okay, so please go to the next slide. So I also love to give this top down from a because this is easy to understand. So we are talking about CMOS technology. Then let's see where the CMOS technology is used. So if you look from the product point of view, let's say I take my laptop. Can you please go back? Yeah. If I take my laptop here, so so if you and inside my laptop, all of you know there's a motherboard and we have different ICs. So I have chosen one IC. Let's say I have an Intel Core i7 IC here. So then this is a packaged part, right? So if you unpack it, you'll find a die, and this die. So in the right hand side here, this is the unpacked die, right? So if you go a little bit down, so if you go to the next slide, uh, so this die actually coming from a wafer, right? So this is actually this is a wafer, so it can be a 200 millimeter wafer or 300 millimeter wafer. So on the die, this microprocessor IC is nothing but a die from this wafer. So each piece of this microprocessor comes from a silicon wafer, and we know that the number of usable microprocessor from a wafer depends on the area of the microprocessor, area of the wafer, and also yield. Okay. So if you go a little bit down, so if you go to the next slide. So if you look at this microprocessor IC, inside the microprocessor IC, we have also different digital blocks. I have logic units, memory, temperature control, ESD, pads, baractors, decoupling IOs. So I have different digital blocks inside the IC, which are actually connected to form this full microprocessor. If you go to the next slide. Yeah, next slide, please. Yeah, so so basically here this is my die. So if I go, this is my digital block that we're talking about from the die. Then if you go inside the digital block, most of the digital blocks are constructed using the universal gates like NAND, NOR, XOR gates. So here I have given a NAND gate, right? So if all of you know, the NAND gate has two PMOS transistors and two NMOS transistors. And if I look at NMOS transistor, then the leftmost part, bottom leftmost part is the transistor, right? So this is the TM picture of TM photograph of a transistor. So what I am telling here is, if you take a product, right, and if you go down and down, right, so finally you will reach a transistor, right? So these MOS transistors are the basic components of a microprocessor, right? So whatever we are talking about the CMOS, the evolution of CMOS technology, so this is mostly because the evolution of MOS transistors with time. So when I talk about MOS transistor, so we have N-type MOS transistor as well as P-type MOS transistor. Okay, so if you go to the next slide. So I'll talk about MOS transistors a bit here. So in the left hand side, this is the dye photograph or TM photograph of a transistor, and the next we are seeing the schematic of the transistor. So this I don't know whether you could see my pointer. So if you from the left hand side, if you go to the next picture, so this is where this is the transistor, and in the transistor we have four terminals like gate, source, drain, and body, and when all these terminals are grounded, right? So basically there is no current flow, right? So in the MOS transistors, as we know, so we have metal oxide semiconductor, but there is also two source and drain regions, and these source and drain regions are highly doped, right? So if I take a cross section, if I look at the energy band diagram from the source and drain side, right? So this top right will shows you the energy band diagram. So here you see we have lot of electrons sitting in the source and drain area, but since there is a barrier, right? So the electrons cannot move, right? So the moment you apply gate voltage, actually this barrier slows down and the electrons go to the channel, go to the substrate, and because of the high electric field, those electrons are accumulated at the surface, right? So once we give the drain voltage, right, then the electrons flow and give you the current, right? So this is the basic operation of a MOS transistor. But as a MOS transistor is an active device, and we are mostly interested in the relation between current and voltage. So basically, transistors convert voltage to current. If you give some voltage, it will give you some current, right? So the current, if I look at the current, current is the drain current. This drain current is nothing but charge into velocity, and we know that charge is nothing but for a NMOS transistor's electron and for a PMOS transistor hole. This charge is a function of both VGS and TOX, and the velocity also a function of if you see the drain to source voltage, gate length, and mobility, right? So so your drain current is actually a function of all these parameters: VGS, VDS, TOX, LG, and mu, right? Okay, so and in the bottom I have write that this is the basic first order equation, current equation of a MOS transistor, right? And the current is a function of VGS and VDS. So if I put it in one point, the change in gate voltage gives you the charge, and your drain voltage gives you the moves those charges, so you get the current. Okay, so if you go to the next slide. So we are using MOS transistors because in the CMOS technology we have we use the transistors for analog and digital circuits. And when you talk about circuits, there are basically multiple type of circuits. So we have digital circuits, analog circuits. We have also circuits, mixed signal circuits. So let's talk about the transistors in digital circuit blocks. So if you think from a digital circuit block, here the transistors are mainly used as switches, right? So here I have taken an example of a CMOS inverter. So we have two transistors, NMOS, PMOS transistors, and these two transistors are used as switches, right? So if the PMOS switch is on, the T2 here, this is on, then your output is connected to VDD. And if your T2 is off and T1 is on, then your output is connected to ground, right? This is how you switch the output node, right? So when you give the input, your output is also switched. But if you look at the figure of merits, right, digital circuit, right? So from the figure of merits point of view, the main thing is your delay, right? If you're giving a signal to the input and how fast this appears at the output. So this delay, and this is a very basic equation that I have written in the left down. So here the delay is nothing but Cn VDD by I on. So Cn is the node capacitance at the output node. So also another figure of merit is energy, because we are doing some work, and we also need to know about the how much energy we spend to do this work. So if you look at the total energy, so let's say you are switching, so you are giving input 0, then output is becoming 1. If you give input 1, output will become 0 in case CMOS inverter. To do this work, so the total energy, if you calculate the how much energy is consumed or how much energy is dissipated, so you could also divide into 3 parts, right? Dynamic, leakage, and standby. So I'll not go through those equations, but if you look at the total energy, I could write down it as Cn VDD square 1 plus 1 by k plus 1 by k T standby by T delay, right? So okay, so here the k is I1 by I off, right? So if you look at this equation, right? So we want to do this work at the minimum energy. So energy will be minimum if this k is high, right? So this k, that's why if you want to use a MOS transistor in digital circuit blocks, we have to make sure that I1 by I off ratio of this transistor should be high, right? As well as this transistor should provide lower capacitance, because the capacitance is a function of width and length. So we should choose a transistor having having lower capacitance. Okay, so if you go to the next slide. So we talked about on current and off current. So this is just a view graph, the on current and off current. So these are the first order equations of on current and off current. And if you look at the on current, so on current is nothing but mu n C ox W by 2 Lg VDD minus V threshold whole square, where Lg is the gate length, W is the width of the transistor. And similarly, we can also write off current as a function of W by Lg. So basically, typically the off current you could write at W by Lg 10 to the power minus 7 plus threshold voltage by sub threshold slope, right? So here you could see that you could increase your on current by changing by reducing the gate length, right? And similarly, off current could be reduced by increasing the gate control, right? So this SS here, the subthreshold swing, is nothing but your gate control. So if you have higher gate control, you will have lower off current. And similarly, the capacitance, as I told you, is a function of W and Lg. So this capacitance could be controlled by actually managing the width and length of the transistor. All right. So if you go to the next slide. But when you talk about analog circuits, right? So analog circuits are totally different from digital ones, right? So here the figure of merit is entirely different, right? So here I have shown a simple amplifier, and here the MOS transistor is used as a voltage controlled current source, right? And we are more concerned about the voltage gain, bandwidth, and gain bandwidth product, right? When you talk about voltage gain, so voltage gain is nothing but GM by GD. In this case, this is a common source amplifier. So GM here is the transconductance and GD is the output conductance, right? So since your transistor is here behaving as a voltage controlled current source, to make it happen, what you do is we bias the transistor in saturation, right? And your bandwidth is nothing but your output conductance by capacitance, and gain bandwidth product is transconductance by capacitance, right? So if you go to the next slide. So if I spare some moment for the transconductance, so the transconductance is nothing but if you vary the voltage around the bias point, how much the current is varying, that delta ID by delta Vg is your transconductance. And if you look at little bit in more detail, from the equation point of view, so your drain current is charge into velocity, which you could write as W Q inversion inversion charge times the drift velocity, because your electrons are moved by drift here, right? And if I do this transconductance, so transconductance is a function of del Q inversion by del Bg, or del mu by del Bg, or del. So your transconductance will be a function of how the Q inversion is changing with gate voltage, how your mobility is changing with gate voltage, or how your lateral electric field is changing with the gate voltage, right? And the lateral electric field again is a function of your gate length. Lower the gate length, you will have higher lateral electric field, which will give you higher velocity and higher current. And if you the change in inversion charge by change in gate voltage, so that is a function of gate control and oxide thickness, right? So if you want to if you want to have a transistor for higher transconductance, let's say you want to build an analog circuit with or build an analog means let's say common source amplifier, any amplifier with higher gain, then you have to make sure that your transconductance is higher. The transconductance can only be higher if your gate control of the transistor is high, or your oxide thickness is low, or you have very high lateral electric field. That means your gate length is low. Okay, so if I go to the next slide. So again, here also I also showed what is the physical meaning of transconductance, because as I told you, in a transistor, I mean when you use a transistor in analog circuit, you bias it in the saturation. So this capital Vg is the capital Vg and capital Vd is the biasing voltages, and with the biasing voltages there is a band diagram. So basically there is a barrier between source and channel, right? When you give a small signal in an amplifier, that barrier changes. So because of this change in barrier, your electrons are injected from source to channel, right? So this change in barrier with gate voltage, this is nothing but a function of gate control and oxide thickness that I was talking about in the last slide. Right. So if you want to increase your transconductance, if you want to increase the figure of merits of analog circuit, or you increase your transconductance, so you have to make sure that your gate control is high, your gate length is low, your oxide thickness is also low. Right. Okay. So coming to the next slide. So we talked about transconductance. Okay. And for the output conductance is a simple function of your gate length and your short channel effects, right? Okay, so if you go to the next slide. Okay, so basically if you think from an analog RF transistors point of view, so these are the figure of merits or attributes of a good analog RF transistors. So we talked about transconductance, we talked about output conductance. There is another thing which is noise. Noise should be low, and the capacitance, because capacitance determines the bandwidth and gain bandwidth product in case of analog RF transistors. So your capacitance should be low, and your transistor should be linear, and the variability is also a major concern for analog transistors. So because when you go to when you think from the circuit point of view, so the circuits are becoming faster and faster with time, and also when you talk about analog circuits, so they also need to process the analog signals faster, right? So for that we have to take care of all these attributes, and all these attributes can only be improved by something called transistor scaling. So we'll talk about transistor scaling in the next slide. Okay, so before we go to the transistor scaling, this part also I talked to you. So because we are talking, we are now, if you look at nowadays, we need to process data because we have a lot of data, right? So from different sensors or from different let's say here. So we have a lot of data, and we need to process those data very at a high speed without consuming much power. So that is one of the goal. So to do this, we need to have circuits which are operating at a high speed, and high speed and at low power. Okay, so go to the next slide. At the same time, we have this ubiquitous computing and Internet of Things are coming in a big way. So in IoTs or ubiquitous computing, we have a lot of sensors generating a lot of analog signals, and we need faster analog signal processing and efficient mixed signal systems. And your IoT systems, actually the computation should happen with zero latency. So it also necessitates edge computing. So these are all the requirements, right? And these requirements are increasing with time, and we'll see how to handle these requirements. If you go to the next slide. So the solutions, like we talked about the requirements. The solution is MOS transistor scaling, right? So we have looked at digital circuits figure of merits, analog circuits figure of merits. We have seen that we could have better figure of merits. Let's say if you talk about digital circuits, you can have lower delay or lower energy if our capacitance is low, or your on current is high, or your off current is low, right? So this can only be possible by MOS transistor scaling, and we do MOS transistor scaling to reduce footprint, to reduce capacitance, and to increase on current by off current ratio, right? So let's talk about what is MOS transistor scaling and how the industry coped with it in last 40 years. So when you look at the CMOS transistor scaling, right? CMOS is there from mid 1970s, like 1975. After 1975, we have CMOS circuits available with us. So, and in the last 40 years, almost 40 years, we have seen 3 stages of scaling, right? So one is until 2002, which is called traditional scaling or Dennard scaling. And from 2002 to 2012, we have a area. I mean, so we have an era where we call it equivalent scaling. And after 2012 till now, we are mostly focused on the transistor footprint scaling, right? So the goal of this scaling is still the same, right? Okay, so coming to the next slide. So let's talk about the traditional scaling. So this shows a layout of simple transistors. So this green region is your active, and your gate is your red lines at the gate. And I have mentioned the length of the transistor, width of the transistor, and this is actually 2 transistors. So there is also called contacted poly pitch. Right. So if I look at the area of the transistor, area of each transistor is nothing but W times Lg, right? When you talk about scaling, the scaling is reducing the dimension of the transistor from all the directions. So this is the traditional Dennard scaling. So if you go to the next slide. So here you see when I talk about traditional scaling, so we scale the transistor from all directions. So basically we scale the transistor. So here the transistor is scaled by a factor of k. All the dimensions are reduced by a factor of k, right? So and if 1 by k, this 1 by k, right, is so in the left hand side. So this is the area of the transistor is W times L. And the right hand side, the area of the transistor is W times L by k square. And in this case, if 1 by k is 0.7, then area of the transistor will reduce by 50%. So this is what we call it Moore's law, right? So if you scale all the dimensions by a factor of 0.7, then the transistor area will reduce by half, right? And this has been proposed by Dennard, and also Moore, also Gordon Moore also predicted his famous Moore's law based on this scaling. Right. So if you go to the next slide. Right. So this is what the technology. Okay. This is what the CMOS technology followed actually. So if you look at in last 40 years, so in the left hand side, so first CMOS technology node was available in 1971. This is a 10 micrometer CMOS technology node. So we started, and now in 21, 22, 5 nanometer CMOS node in production, 5 nanometer CMOS technology production. So this is how the industry has progressed over the years, right? So and these names, right? So if you look at this table, sorry, I do not have a pointer here, but if you look at this table, so in the left hand side you have the names of these nodes. In the right hand side, okay, so there is a spelling mistake. So there is a year of production, right? So you see, if you look at the left hand side, right? So this is the node name, right? So this node name, this is just a purely name, right? And this name is nothing but 0.7 scaling, right? So let's say let's take the 800 micrometer or 3 micrometer node, right? So 3 micrometer into 0.7 is 2.1. We name it as 2 micrometers. So this is how the naming convention has been used, right? So 2 to 1.5 is also 0.7 times scaling. 1.5 into 0.7 is 1.05. So we named it 1 micrometer node. So similarly, like in 2009, we have 32 nanometer node, and we move to 22 nanometer node next. Then 15 is at just 0.7 x 0.7 scaling, right? Right. So the aim of showing this here is just to tell that this naming convention is coming only from the 0.7x, right? 0.7 times scaling, right? It doesn't have to do anything with the dimension of the transistors. So in 2023, so currently we have 5 nanometer CMOS node in production. So we have products coming with 5 nanometer CMOS technology. And there are a lot of research going on in 3 nanometer CMOS node. Actually, the Samsung, TSMC, they are actually trying very hard to have 3 nanometer CMOS node production in 2023. And after 3 nanometer CMOS node, we'll move to 2 nanometer CMOS node. Okay. Okay, so so we talked about the CMOS technology node. So these are the naming convention. But if you look at the length, right? So here, how the transistor length has scaled over the years. So you look at this blue line. So actually, in the beginning, we are following Dennard scaling. So actually, your every year there is a reduction in length. Length was reducing by a factor of 0.7. So this has followed till early 2000, right? So around 2002, we could scale the gate length, right? After that, because of some reasons, I'll talk about that. We could not scale the gate length. Then the gate length actually saturated. If you look at this blue dots here, so there is a reduction in gate length till 2002. After 2002, there is a, the slope of reduction of gate length reduced, right? Okay, so if you go to the next slide, the next slide shows the minimum gate length for different technology nodes. So this also tells you the same thing. So we could scale very well till 65 nanometer node, right? So if you see, the gate length was reducing with every node, but after 65 nanometer node, there is a saturation. So you could not really scale the gate length properly, right? But the node name is still the same. Node name, we always follow the 0.7x. But if you look at the minimum gate length available in the technology node, they are actually different, right? So that was my point, right? So node name, when we talk about 45 nanometer CMOS node, it does not tell you that 45 nanometer is the minimum gate length. The minimum gate length shown in this chart is around 32 nanometer for a 45 nanometer CMOS technology. And similarly, when you're talking about 10 nanometer CMOS technology, so minimum gate length is around 15-16 nanometer, right? So we cannot really go to 10 nanometer gate length in 10 nanometer CMOS node. Okay, so currently the physical gate length is always higher than the technology node. So actually the node name does not carry anything nowadays. All right, so if you go to the next slide here. So this is the main motto behind the scaling. So we are talking about CMOS technology scaling from last 40 years. So we do scaling for power, performance, area, cost. These are the 4 guidelines, right? So we do scaling to reduce power, increase performance, reduce area, and reduce cost, right? This is the main motivation behind the scaling. Okay, so if you go to the next slide. Okay, so to summarize, when we talk about CMOS technology scaling, we talk about pitch scaling, right? So all the dimension will reduce by 0.7, will reduce by factor of 0.7, right? So that area reduces by almost 50% in every node. So this is what the traditional Dennard scaling, and so this is called the pitch scaling, right? So one idea of scaling is to reduce the active area of a transistor, right? So when you reduce the active area of a transistor, that means in the same area, we could have more number of transistors. As I shown you in this, I compared Pentium 2 and Intel i9. So the density of the transistor is increased because of this pitch scaling, right? So the scaling of the active area of a transistor. But another main goal is the performance, right? So every CMOS technology node, let's say we are in 45 nanometer, we want to move to 32 nanometer CMOS node. So 45 to 32 is not only the area scaling, right? 45 to 32, the performance of the transistor should also improve, right? So in the Dennard scaling area, during Dennard scaling, the gate length was reduced with scaling, right? Reduction in gate length also improved on current and off current, right? So the point is, we are not only focused on area scaling. Yeah, that is fine. We need to reduce the area of the transistor. At the same time, we also need performance, right? And the performance of any technology node is basically shown by something called universal curve, right? So universal curve, if you whenever a foundry releases a new technology node, they also release the universal curve of that node, right? So this is nothing but a plot between off current and on current, right? So they measure on current of the nominal transistor, subnominal, supernominal transistor, and off current of those transistors. Then the plot, right? And actually, here the y-axis is log axis and the x-axis is linear axis. And if you plot it in this way, this will be a straight line, right? And actually, this universal curve tells you how good is your technology node, right? So if I'm comparing, let's say 45 nanometer CMOS technology from Intel or 45 nanometer CMOS technology for TSMC, what I have to do is I have to just plot the universal curve of both of these technologies, and then I'll tell you, okay, which is a better technology in between this Intel and TSMC. Right. So universal curve is very important. So if I go to the next slide here, yeah. So so here I have shown the two universal curves, the same thing. So in the last 25 years, actually our universal curve has shifted towards the right, right? If you see left-hand side plot, if you talk about on current at the same off current, right? So let's say you keep the power same, and at the same power, we are able to get 6 times more on current. Same IF, we are able to get 6 times more on current, and so that means 6 times more on current means 6 times more performance, right? So so this is what it is. Then if you look at the right hand side, okay, fine. If you do not look at the same off current, let's say you'll keep the performance of the transistor same, right? So if you keep the on current same, that means your x-axis is same. Then you'll see that in last 25 years, the off current has reduced by 5 orders of magnitude at the same on current, right? So this is the beauty of CMOS technology scaling, right? So we could scale area, at the same time we could move the universal curve to the right. So actually, because of this scaling, right? So at the same off current, we could get very high on current, or the same on current, we could get very low off current. That enabled a lot of applications, right? So you see, I always tell my students, why? Because why the mobile phones that we're talking about, right? So we have all handheld devices. Why does it come only in means late 2000s, right? Let's say around 2005 and 2010, we'll see a lot of handheld devices are coming into picture. This is because we have a technology available where at the same performance we can have very low off current, right? So we could have the same performance at very low power, right? So actually the scaling enabled this. Okay, so if you go to the next slide here. Okay, so Dennard scaling till 2002, actually we started scaling the gate length, right? We continuously scaling the gate length. Because of gate length scaling, your universal curve shifted towards the right, right? But how low you can go with the gate length, right? So there is a fundamental issue because the MOS transistor operates on the basis of gate control, right? But if you reduce the gate length, your drain competes with the gate to control the source to channel barrier, right? And stronger drain control actually increases your off current and degrades subthreshold behavior, right? So we need to avoid that, right? So that's the reason we cannot really reduce the gate length, right? So to increase the gate control, that can only be done by reducing the oxide thickness, right? So you have this oxide thickness here, metal oxide semiconductor. So between metal and semiconductor, we have a insulator, and the thickness of the insulator is very important, right? So if you are reducing the gate length, right, then to increase the gate control, we have to simultaneously reduce the oxide thickness, right? So gate length scaling goes hand in hand with oxide thickness scaling. Right? Okay, so if you go to the next slide. Yeah, next one. So here you see, okay. So here you see with the Dennard scaling, so which is very well followed till 130 nanometer. So here you see your gate length is scaled. At the same time, your oxide thickness is scaled so that your gate control is still kept intact, right? But if you see, the oxide thickness scaling basically stopped at 90 nanometer CMOS node, right? So 90 nanometer CMOS node, the oxide thickness is almost very close to physical thickness of the oxide is very close to 1.5 nanometers, right? So with a very thin oxide, so we started seeing higher gate leakage because the oxide becomes very thin. Because of the thin oxide, the electrons could quantum mechanically tunnel from channel to gate, and this gives rise to higher gate current, right? And higher gate current is higher power dissipation or a higher energy, right? So that's the reason we cannot go below 1.5 nanometer of oxide thickness. Since oxide thickness we could not scale the gate length. That is the main reason why the Dennard scaling stopped around 2002, because we could not scale the oxide thickness, so we could not scale the gate length. Okay, so going to the next slide. And on top of that, when you reduce the oxide thickness, that means your gate is coming closer to the channel. It gives better gate control, but because of lower oxide thickness, your effective electric field also increases, right? And because of effective electric field, you have okay. So there is not only the reduction in oxide thickness, there is also increase in substrate doping to take care of the short channel effects. So this higher substrate doping, reduced oxide thickness actually increases your effective electric field. So effective electric field actually increases the scattering events and also decreases the mobility, right? Think about a transistor. Your electron is going from source to drain, right? Electron is going from source, it is starting from the source and going from source to drain. But if there is a very high electric field, transverse electric field, then these electrons cannot easily flow. They will interact with the interface, they will interact among themselves. These are called the scattering events, right? Because of these scattering events, so their mobility reduces, right? And this is experimentally shown that higher electric field reduces the mobility, right? So this is one of the disadvantages of technology scaling. So actually with technology scaling, your intrinsic mobility of electrons and holes are also reduced, right? So we are talking about the electron mobility of 1350 centimeter square per volt second, but in scale devices, it hardly is around 200-300 centimeter square per volt second. This is because of different scattering events. Okay, so going to the next slide. So why the Dennard scaling stopped in 2002? So there are several issues. One is mobility of electrons and holes are not very high for scale transistors, right? Oxide thickness could not be scaled because of gate leakage issue. Because since oxide could not be scaled, your gate length could not be scaled, right? But we cannot stop there, right? So we have to move our universal curve right, because we have to continue gate scaling. We have to continue our transistor scaling. So to do that, so this started. We started to have new innovations, and the Dennard scaling stopped. We started the equivalent scaling, right? I'll talk about equivalent scaling. If you go to the next slide. Okay, so what is equivalent scaling, right? So let's think about the current, right? So because we want to have higher on current every new node, right? Every new CMOS node, right? So if you look at the current, so current is nothing but charge into velocity, right? I talked about it earlier. So current is charge into velocity. So actually, when you are scaling the gate length and your velocity was increasing, right? And when you are scaling the oxide thickness, your gate is coming closer to your channel and your Cox is increasing, oxide capacitance is increasing, and your charge is increasing. That's why you are having higher current, right? So we could increase the current by length and oxide thickness scaling. So this is what the Dennard scaling. But it stopped in 2002. We could not do that because oxide thickness, oxide we could not scale, so gate length we could not scale. So then the industry professionals come with some new innovation. One is strand silicon, right? So okay, fine, we cannot scale oxide thickness, we cannot scale gate length, but let's say I have other ways to increase mobility, right? Let's say if I increase the mobility, if I could find a way to increase the mobility of the transistor, then your current will also increase. So mobility increases, your velocity will increase and your current will increase. And also we could increase the charge by increasing the capacitance. We will not use, so basically till 2000, because till 2000, okay, I'll come to that point. So we are in the beginning, we are using silicon dioxide. Then the industry moved to high K metal gate. The high K metal gate, the higher K dielectric provides higher oxide capacitance, and also higher oxide capacitance means higher charge, and we could have higher current also, right? So going to the next slide. So these are the strain engineering. So people started talking about strain engineering from early 2000, right? Right. So and the strain engineering. So basically, if you have your semiconductor, so let's say silicon have a lattice constant, right? So let's say if you change the lattice constant, right? So if you change the lattice constant, the mobility of electrons holes will change, right? So it is observed that if you give the tensile stress, right, that means if you increase the lattice constant of semiconductor or silicon, then the mobility of electrons increase, and if you compress, if you reduce the lattice constant, mobility of holes increase. So that is observed experimentally, and people started using it, right? So if you go to the next slide, right? So in 90 nanometer CMOS node, for the very first time, we have used this dual stress layer. So this dual stress layer is deposited by PCVD by applied. So there are tools available from Applied Materials Novellus system. So this dual stress layer, that means what you did is you deposited a tensile stress layer on top of your NMOS and a compressive stress layer on top of a PMOS, right? So because of these stress layers, so it provides the tensile strain to the channel in case of NMOS and compressive strain to the channel in case of PMOS, right? So because of the stress, your mobility improves, and if you see there is a shift in the universal curve, right? So our main goal was to shift the universal curve from curve towards right, and that the stress layers could do that. So here you could see the view graphs, also TM pictures of this tensile stress layers. So that has been used since 90 nanometer CMOS technology, and we also have done some experiments in our lab at IIT Gandhinagar. So here I have plotted the universal curves of the transistors with different stress, right? So 1.8 gigapascal means this is tensile stress, minus 3.8 gigapascal, that is compressive stress, right? So if you give so NMOS transistor, if you give different stress, you could see there is a shift in the universal curve, right? So this technology, this innovation is used for the first time in 90 nanometer CMOS node. If you go to the next slide, right? So actually the stress layers give benefit. So you could get same off current, better on current, or same on current, better off current, right? So please keep in mind, this is done without changing the gate length, without changing the oxide thickness, right? By using stress layers, you could move the universal curve and you could make better performance at the same power. All right, next slide. Okay. So what happens is okay, so we started using stress layers in 90 nanometer CMOS technology node. Then we moved from 90 to 65, 65 to 45. Then we figured out that stress is not giving more benefit, right? So since stress is not giving more benefit, then the industry moved to something more innovation. So they have started replacing the silicon oxide they have started replacing silicon oxide by another gate dielectric. So if you go to the next slide, I'll talk about it. So in 45 nanometer CMOS node, industry moved from silicon dioxide to hafnium dioxide, right? So hafnium dioxide has a higher dielectric constant, right? So if you look at this here, the silicon dioxide has a dielectric constant of around 3.9. Hafnium dioxide has a dielectric constant of around 20. So when you have a higher dielectric constant, and if the physical thickness of the dielectric is the same, then the capacitance will be more, right? Higher capacitance means higher charge, right? Higher charge. So that means at the same thickness, right, you could get higher charge because your capacitance is increased, right? And also, since your capacitance increases, your gate control increased, right? If your gate control increases, then you could scale the gate length. You could reduce the gate length. See why you cannot reduce the gate length? Because when you reduce the gate length, we have to reduce the oxide thickness, right? But oxide thickness we could not reduce because of gate leakage current, so gate length could not be reduced. Now, by using high K gate dielectric, your oxide capacitance increases. That means we have more gate control, right? This enabled the gate length scaling again. Okay, so going to the next slide. And on top of that, because this is a different dielectric, high K dielectric, so if you want to keep the oxide capacitance same, you could increase the thickness of the dielectric, right? So it serves in two ways. So actually it reduced the gate leakage, also it increased the gate control. So there is an experiment done, and actually gate leakage reduced by 25 times for NMOS and 1000x times for PMOS, 1000 times for PMOS, right? Okay, with the introduction of high K metal gate. So why metal gate? Because we are using now hafnium dioxide, right? And hafnium dioxide, actually the traditional silicon dioxide is a furnace grown process, right? But when you introduce high K metal gate or hafnium dioxide is deposited, right? And traditionally our gate was made of polysilicon, right? But the polysilicon is not compatible to hafnium dioxide. So when you started depositing polysilicon on top of hafnium dioxide, so you used to see a lot of defects, right? So because of that, industry moved from polysilicon to metal, right? So basically, we started using metals like titanium nitride, tantalum nitride in case of in high K metal gate technology, starting 45 nanometer CMOS node. Okay, so going to the next slide. Okay, so this is this I have taken from Intel's slides. You could see that if you look, 45 nanometer is introduced. 45 nanometer, sorry, high K metal gate technology is introduced in 45 nanometer CMOS node, and they could, because of introduction of high K metal gate, they could scale the gate length. Because of scaling of the gate length and increasing oxide capacitance, you could move the universal curve from to the right, and this has also because this has also continued in 32 nanometer CMOS node. You could see there is a continuous. They could show the shift in universal curve, right? And they could actually scale the transistors, right? Okay. Okay, but the issues with high K metal gate, there are several issues with high K metal gate. And if you talk about hafnium dioxide is not a very good dielectric like silicon dioxide. And they have a lot of defects. So basically, there are a lot of research how to control the defects in the hafnium dioxide. So a lot of research also going on nowadays, means still now, to reduce the defects in hafnium dioxide, right? But because of defects in hafnium dioxide, also we saw some improvement in device performance. So if you go to my next slide, so there are oxygen vacancies, basically oxygen vacancies in hafnium dioxide. So if you go to the next slide, so these oxygen vacancies also helped in improving the mobility, right? So because of oxygen vacancies, we could see the reduction. You could see the remote Coulomb scattering, the reduction in remote Coulomb scattering. And because of modulation in remote Coulomb scattering, so you could see different width devices give different mobility. So that has been used in several ways in different digital circuits or analog circuits. Okay. Okay. So then, okay, so till 32 nanometer CMOS node, we are using planar technologies, right? So if you look at this picture here, so we started using high-k metal gate. We started using strain, process induced strain, right? See this red, the source and drain. We do not have traditional source and drain, so silicon. So these are silicon germanium source and drains, which gives actually the strain to the channel. But see, we used high-k metal gate, we used strain, still we could not really scale the transistors properly. So and we started seeing the limitations when you go to the very scaled dimensions like in 32 nanometer CMOS node. So so then industry suddenly moved from planar technologies to 3D. I mean basically the 3D transistors, right, like FinFETs. So our equivalent scaling actually stopped here. So when I talk about equivalent scaling is enabling scaling with stress layer, stress and strain, or high-k metal gate, right? Okay, if you go to next slide. So then we moved in 2012. We moved to something called from equivalent scaling to footprint scaling. So our goal is to have higher performance, but then we thought, okay, we could not improve the performance of the transistors by scaling. So we then invented another parameter called performance per footprint, right? So if you increase performance per footprint, then this will also serve the purpose. So this footprint scaling started in 2012, right, and it is still continuing. Okay. So coming back to the footprint scaling, right? So if you see, this is a CMOS standard cell. I think all of you are aware of a standard cell. The standard cell has both NMOS and PMOS regions separated by N to P spacing. The poly lines are running vertically here, and the metal lines are running horizontally. The CPP, the contacted poly pitch that I talked about, is gate length plus poly to poly spacing. Sorry, I could not have the pointer, but you could read the CPP. This contacted poly pitch is gate length plus poly to poly spacing, and the metal pitch is nothing but metal width and metal to metal spacing. And so this is actually the area of a CMOS standard cell. So a standard cell. And this is actually the footprint. If I talk about the footprint of this cell, this is nothing but we could talk about the CPP and MP, right? So the footprint is determined by the contacted poly pitch and the metal pitch. And also we defined terms called track height, right? So track height is nothing but it tells you how much metal tracks are there in the standard cell. If you go to next slide. So if you look in more details, the recent CMOS scaling challenges. So there is so basically, if you so we are still addicted to this Moore's law, right? Because Moore's law Dennard scaling, which tells you that the area will reduce by half in every new CMOS node, right? So let's say I go from 40 nanometer to 10 nanometer CMOS node or 7. So 14 nanometer to 10 nanometer CMOS node, your areas will reduce by half, right? So, what was done before is mostly we are reducing the footprint by reducing the contacted poly pitch, right? But we have seen lately that contacted poly pitch is the scaling of the contacted poly pitch is slowing down, so it is not meeting the target. So then we thought, okay, what will happen if you scale the metal pitch, right? Instead of scaling the with the contacted poly pitch scaling, we started thinking about metal pitch scaling, right? Please go to the next slide. So then, so contacted, so basically now we thought, okay, if you look at the footprint, right? So here I have compared two pictures. One is our planar structure. Here the effective width per footprint is 1. But if you look at a 3D structure, so basically here in the 3D structure case, so we have like FinFETs, right? So basically you have you have 3D structure. So basically your channel is not planar. So channel is now you have a vertical channel. So if you look at the right hand side picture, so this is actually structure of a FinFET, right? So we call it tri-gate device, sometimes FinFET or multiple gate technology. So here your source and drain, so you have a pin and your pin is your channel, right? And your gate is surrounding this pin, right? So in this case, you see, if you look at, right, so compared with the planar structure we have only one surface, but in the pin we have two surfaces, right? So if you look at the footprint, the effective width or footprint has increased by twice when you move from planar to FinFET based technology, right? Go to the next slide. And we started adopting this FinFET based CMOS technology in 2012 with 22 nanometer CMOS node. And this FinFET based technologies has several advantages. So here you can see the channel is surrounded by gate from all three sides, so it has very good gate control. So once it has very good gate control, that means we could scale the gate length, right? So see, gate length we could not scale because the gate control was weak, right? Now since the gate is surrounding your channel, that is, we have a very good gate control. So we could now with FinFET we started again scaling the gate length, right? Okay, so if you go to the next slide. So FinFET has several advantages. People saw increase in on current, POR area, increase in transconductance, POR footprint. I'll call it footprint. So we have more current per footprint, on current per footprint. We have more transconductance per footprint. But there are some issues like quantized channel width, which is not that easy for the analog designers, analog circuit designers. But we saw lesser debul, higher lesser drain barrel lowering, which gives you higher output conductance also. And since your body, because body is low doped body, almost intrinsic body, no doping, and also there is so we don't see, because of low doped body, you don't see any body effect. And since the doping is not there, so also we observed lower random dopant fluctuations. But there are some issues with the parasitics. I'll come to those points later. So okay, going to the next slide. So with the invention of FinFET, right, with the introduction of FinFET, we thought that we could start doing the metal pitch scaling, right? Right. So okay, so go to the next slide, please. So this shows a FinFET based standard cell. So in a FinFET based standard cell, the NMOS and PMOS area has fins with a particular fin pitch, right? So if you see here, there are two fins for NMOS, there are two fins for PMOS. The fin pitch is defined by fin width and fin to fin spacing. So in this case, the track height scaling has one problem, which is the fin depopulation, right? So basically, since we have the metal pitch, right, the track height is now determined by number of fins, right? Number of fins. So if you want to do track height scaling or metal pitch scaling or track height scaling, then we could only do it by fin depopulation, something called fin depopulation. So if you go to the next slide, I will talk about what is fin depopulation. So this slide shows fin depopulation. So with fin depopulation, the number of fins in the standard cell reduces from 4 to 3 to 2. Probably in future, we have to reduce the number of fins to 1. So so we have so starting from 22 nanometer CMOS node, where we introduced FinFET. So after that, we are constantly depopulating the fins, right? So this is just to enable the smaller track height and smaller footprint of the standard cell. Okay, so go to the next slide. So this the fin depopulation actually degrades the device performance, right? So what do you mean by fin depopulations? So the number of, let's say we have this NMOS transistor, so we have 4 fins, right? So in the 4 fins means each fin is carrying current. So we have higher on current, right? Now we have started reducing the fins, number of fins. So when you started reducing the number of fins, it led to drive current degradation, on current degradation, right? So to avoid that, so what industry does is industry increases the height of the fins, right? So if you see the 22 nanometer technology, so this is how the fin looking like. But 22 nanometer to 40 nanometer to 10 nanometer, that's because we are depopulating, the number of fins is reducing in a standard cell. To reduce the drive current degradation, we increase the fin height, right? And the fin profile, there are a lot of work also went into fin profile. So we started having thinner, straighter, and taller fins. So these are done to take care of the fin depopulation, right? Okay, the next slide. Okay, so going by the scaling trend, the track height only allows a single fin in 3 nanometer CMOS node and beyond. The performance degradation with a single fin could not be recovered by fin height increase, right? So if you see here, you see going from 14 nanometer CMOS node to 3 nanometer, 5 nanometer CMOS node, we have gone from 7.5 track to almost 6 track, right? Right. So 6 track. If you look, we have 3 fins in a standard cell. Now we have reduced to 2 fins, right? And in future, if you want to go, if you continue like that, then we have to go from 6 track to 5 track, right? 5 track will only allow only one fin for NMOS, one fin for PMOS, right? When we have one fin for NMOS, one fin for PMOS, and there is a limitation on track height, means limitation in the fin height scaling, you cannot really make the fin very tall, right? So then we have process limitation. So because of limitation in fin height, the single fin devices have very lower on current because we have only one fin, right? So then, okay, if you go to the next slide. Yeah, next one. Okay, so there are several challenges. I'll skip this slide. Okay, if you go to the next slide. Right. So then in after 5 nanometer, so when 5 nanometer uses 6 track, right? So after 5 nanometer, where you're using 2 fin per standard cell, then we supposed to go to the single fin per standard cell, but single fin per standard cell has lower drive performance, drive strength. So then we thought, okay, then let's look it in a different way. So instead of having fins, if you have seats, nano seats, and if you use stacked nano seats, right? Let's say we have seats, then we could increase the current or we increase the drive strength by having multiple number of seats on top of each other, right? So this started our nano seat FET architecture, and nano seat FET architecture is will be introduced in 3 nanometer CMOS node. There are a lot of research going on. We do not have any product in the market with the 3 nanometer CMOS node, but it will come with nanosheet FETs in future. So, okay, if you go to the next slide. So the advantage of nanosheet FETs, if you look at these two pictures here, so the fin FET, let's say we have two fin FET with 2 fin in the standard cell. So W effective per footprint is 4 because we have 4 surfaces, right? Fin FETs are 4 surfaces, right? But in nanosheet FET, we could have multiple seats on top of each other. So here with 3 seats, then W effective per footprint can be increased, right? So that's why it's called footprint scaling, right? Here we are not doing anything else, but just by increasing the number of seats, we are increasing the drive strength per footprint, right? So this, okay, so if you go to the next slide. Okay, so this nanosheet architecture is now is planned to be used for high performance computing. So the advantage is more number of transistors in the same area, higher functionality, higher on current for the same width effective or width by length effective, and improved because the other advantage of nanosheet FETs is your gate is all around, right? All right. You could hear me now?
Yes, sir. Yes, sir. You can go on.
Yeah. So, okay. I'm very sorry. I don't know what happened. Okay. So, how do you go to the full screen? Okay. Okay. So, I think you could go to the previous slide. Hello. All right. Um, okay. So, in nanoseed FETs, also you could increase the number of seats. So if you could increase the more seat count, increases the effective width for layout footprint. So uh, it is means also it has advantages compared to FinFETs. FinFETs really there was a difficulty in increasing the performance or ion with footprint, but in the nanoseed FETs we could do that. Okay, if you go to the next slide. Okay, so fine. So there are still a lot of issues which the industry is facing, and they are working on it. One is fine. So we could increase the number of seats, but with increasing the number of seats, there is an issue with the parasitic capacitances. So here I have seen just the Miller cap, the CGD. So because because see, if you look at this left bottom graph, there is a connection between gate metal and the drain, right? So and this actually creates a lot of increases the Miller cap and the performance of the circuits. So that could be reduced, that could be optimized by reducing the distance between two nanosets, which industry is currently working. But by reducing the distance, means there are process issues, right? So because you have to deposit metal, and how will you do it with a reduction on the, so that is a question mark. Okay, so if you go to the next slide, I think I should. Also, number of seats per stack, people have shown that when you stack the number of seats on top of each other, more number of seats, so you have issues with access resistance, right? So bottom seat is, but the resistance between the top contact is at the top, right? So resistance between the contact and the bottom seat, the access resistance increases, and it also creates issues. So this is one of the thing also, a lot of because a lot of industry professionals are working on it, how to improve the access resistance. Yeah. Okay. Going to the next. Right. So this is a major issue. We are also currently working on it. This is the imbalance, an NFET PFET imbalance, right? So in FinFET, because before nanoseed FETs, we are working on FinFET based CMOS technology. In the FinFET, your electrons are flowing at the wall, right? In the wall, right? So basically, if you look at the wall, the semiconductor wall, so this is 110 surface, and the direction was 110. But in the nanoseed FETs, actually the electrons are flowing around 100 crystallographic surface, right? On 110 direction. So the surface orientation has changed. So because of the surface orientation issue, so there is a imbalance between NFET and PFET, right? So PFET loves 110 surface orientation. Sorry, the whole transport is better in 110 surface orientation. Electron transport is better in 100 surface orientation. But in case of nanoseed FETs, since the holes are also flowing in the 110 surface orientation, 100 surface orientation, so there is an imbalance, right? So if you go to the next slide, I'll tell you what is that. So here you see when you go from FinFET to nanoseed FETs, the electron mobility improves, but the whole mobility reduces, right? So that is an issue, because if you look at the drive strength of NMOS has increased compared to the drive strength of PMOS. Right. So this is a big issue, and there are a lot of research going on how to make sure that PMOS drive strength is also better. because if you have NMOS PMOS drive strength imbalance, then you have to also think about different widths, and it will increase your footprint. Okay. Next slide, please. Okay, so this is how the transistors are evolved till today. So from 90 nanometer, if you look the transistor, how the real transistor look like from 90 nanometer all the way to 3 nanometer. So they look different in every node, right? So 90 to 65, they are still with silicon dioxide with strain. But when you move from 65 to 45, we introduce high-k metal gate. So transistors look different. 4532 has high-k metal gate technology. Then when you move from 30 to 22, we moved from planar structure to 3D structure. Then 22 all the way up to 5 nanometer, we continued with the FinFET. Then from 3 nanometer, we are moving to nano FinFETs, and they look entirely different, right? But one thing is very common, to note here is device area is only reducing because of pitch scaling. Nowadays, we are only talking about footprint scaling, right? So we could not really reduce the gate length much. We could not reduce the oxide thickness much. The performance is improving by footprint scaling. Okay. So innovation. So this slide, this is a very recent slide. So basically, you could show that the innovations, how the innovations drove the CMOS scaling. So from 90 nanometer node all the way to 3 nanometer, we are also talking about 2 nanometer CMOS node, 1 nanometer. So you could go through. So you could look at this slide. So if you see from the architecture, we have moved from planar to FinFET. Now we're talking about nanosheet gate-all-around transistors. And in the future, we may go to 2D FETs, like 2D two-dimensional transistors, right? So industry is having a lot of innovations, right? And the main point of this slide is actually the innovations are driving the scaling. And I hope it will also drive scaling to the nodes, right? Okay, then go to the next slide, please. But there are issues. The issue is process variability, because that is a major issue nowadays. Because of processing, the process variability, because if you measure the transistor, same transistor at different places on the wafer, so you'll get different characteristics. So that variability, a lot of research happening on to control the variability. If I go to the next slide, so we have done also some work on variability. So here you could see we have measured 200 FinFETs, 200 similar FinFETs, right? So you could see in our lab here, so we have measured 200 similar FinFETs. So when you measure the same FinFET, you see there is a huge variation in threshold voltage on current. That is actually what is the fact for now, right? So we have the variability is a bigger issue. And this variability is going to increase in future CMOS nodes, right? So a lot of research happening, and to at least control this variability. If you do not control this variability, then it will be very difficult to design with these transistors, because we have to have a very good PDK to make sure that it takes variability into account, right? Which is not that easy. Okay. And this is a very recent issue. This is an article I just read few days back. The cost per wafer, right? See, why means the main motivation of CMOS technology scaling was cost, right? But now, if you look, this is just a TSMC from the TSMC. TSMC just published recently. So this is the cost per wafer in dollars, right? So 3 nanometer, a single wafer will cost $20,000. Right? It is like, I mean, it is huge, right? So basically, there is a lot of debate happening whether technology scaling is giving us whatever we want. Because if you look at the cost per wafer is increasing. It's a good thing that we have more number of dies in the same wafer. So if you divide the total cost by total number of dies coming out of that technology node, then the cost increase is reduced. But This is a thing which need to be worried because this is a worrying thing. This is because the complexity in processes, the tools, and all other things. So an industry is working on it, and I hope in future the cost per wafer will not increase. It will stabilize or it will decrease. Right? Okay. So next slide. So this is my final slide. So basically, we talked about CMOS technology scaling over the years. So here we have planar structure. In the left hand side, we move to FinFET, nanosheet FETs now, and in the future we'll go to 2D 2D electronics. We'll use two-dimensional materials. So it will no longer be silicon. This is already in the IRDS roadmap that will move to molybdenum disulfide or tungsten disulfide 2D materials. Actually, the conferences, TSMC, Intel, Samsung has already shown the transistors working with tungsten disulfide transistors, and that is already in the roadmap for 2030 or beyond. So to summarize, CMOS technology scaling augmented with innovation in transistor architecture will continue for next 20 years. I don't see the technology scaling dying, so it will continue at least till to 2040. The process integration innovations are the essential enablers to keep the power, performance, area, cost improvement from node to node. The process variability and other small dimensional effects will be the roadblock and need to be addressed through process technology innovations, right? So there are a lot of research happening in this area. Cost per wafer and chip prices will increase unless there are multiple foundries producing the same technology. So this is a bigger issue now. So there are only 2 or 3 foundries who are working on the advanced CMOS technology nodes. We could actually name them. One is TSMC, other one is Samsung and Intel. Nobody else is actually working on 3 nanometer, 5 nanometer CMOS nodes, right? So so this is actually increasing the cost per wafer because of the monopolistic view. So chip prices are increasing. I hope there will be multiple foundries producing advanced CMOS technologies, which will keep the chip prices down. With this, I'll finish this talk, and thank you all. And I understand it did not go well because of lot of disturbances. I was not. I don't know whether I was not very conversant with Microsoft Teams, so it took some time. And please excuse me for this. And pretty sure in future I could have a better talk. Right? Okay. So with that, I'll stop here. So any questions I'll take, or I don't know. Yeah, if there are any questions.
So you can take question from question and answer.
No, I could not see that Q&A. Yes,
So the first question is, what happens to delay if we increase load capacitance?
No, what was delay? So if you increase load capacitance, your delay will increase, right? So that is the main point, right? So what we're trying to do now is we are trying to reduce the node capacitances, right? And the node capacitance could only be decreased if we scale it, right? So when you're going to these 3D transistors, because of the 3D structure, your node capacitance is increasing. So that is actually a issue which industry is facing, and they're trying to reduce it with different technology innovations.
Okay. Next is, as we know that government is looking to build ecosystem in India, so wanted to understand where we are now in brief and who are working from the public and private space. Also, please help us in understanding key raw material that is required to have a successful CMOS ecosystem in India.
I mean, basically, from the manufacturing point of view, India is nowhere, so we are not manufacturing. I mean, so we do not have a CMOS technology fab, CMOS fab in India. We have only 180 nanometer strategic fab in SCL and Semiconductor Lab Chandigarh. If you think from Indian point of view, it is very difficult, as I told you, right? So this 5 nanometer, 3 nanometer CMOS fabs will be super expensive, right? And it needs lot of know-how. And I do not know, even if we have money, somebody will give us this technology in India. But from the India point of view, we could start with like 45 nanometer, 28 nanometer CMOS nodes. A lot of chips are fabricated also in 28 nanometer, 45 nanometer CMOS nodes now. And if you think from analog and mixed signal circuit point of view, they are totally dependent on 45, 65 nanometer nodes now, right? So we could start with 45 nanometer, 28 nanometer CMOS nodes, and we could plan to, go to 7 nanometer, 5 nanometer CMOS nodes in future. Yeah, so my view is that we should not really directly go to 7 nanometer, 5 nanometer CMOS nodes. We should start with a smaller node and then go to other nodes in future.
So we are done with the questions, and thank you, Dr. Nihar Mohapatra, for sharing your valuable knowledge on CMOS technologies.
So
Yeah,
Dipesh,
so yeah, thank you. But
initially found some glitch at the technical side, but the end was a presentation and the contents are very well presented. So questions, answers are also with us. We have already replied most questions.
yeah, I'm sorry. I don't know what happened because it also broke my flow because I was little bit not very happy with this.
Presentation contents and all that's very nicely presented, viewed by the audience. So we'll be share the recordings and everything with you also in upcoming times.
Yeah, sure. I think next time if I speak, I have to be very careful about this online meeting.
Yeah, sure. It's so initial was a glitch, but it's everything done well afterward. Thank you, sir, for sparing your time.
Yeah, thank you. Okay.
So, sir, there is a audience attendees that asking the contact details.
Oh, sure. You could give my email ID. So I think my means if you go to IIT Gandhinagar website and my email ID is there, Nihar NIHAR at IIT Gandhinagar IITGN.ac.in. Right.
Yeah. So on the website in that's it's available. Fine. Yeah.
Okay, so I hope we'll meet face to face with all the attendees sometime.
Sure.
Yeah. So before you end, so again my apologies for these glitches. I'm not very happy with this, but this is how it is, right? So
it's fine. The presentation and everything was done excellent. Its contents are there very up to the marks. It's fine. Thank you, sir. Thank you.
Okay.
Yeah.